Okay, good evening, one and all. Okay, good afternoon. Sorry. Last class we have been discussing about MD4 hashing algorithm, right? We saw how the input message blocks have been made register words. What do you mean by register words? And we'll be taking 4 register words as output. We just saw, and this is the way we'll be taking the 4 outputs here. And we also saw the Boolean function and how the padding is done, right? And at last we concluded with the 3 Boolean functions and how, and sorry, where these Boolean functions are going to be used. That is for, we have 3 rounds, round 1, 2 and 3. Each round made up of 16 steps. So for first round, this will be a Boolean function and the respective round constant. And these are the 2 rounds Boolean functions and the constants, right? Now we move on to what is happening under each and every step of a MD4. Okay. So if you take each and every step of a MD4, they are going to produce the 32-bit register value. That is, we are going to get one registered word that is A is going to be computed for each and every step for all the 48 steps, and based on this rule, right? So if, for example, if you are going to take compute AI, okay, you'll be using AI minus 4, I minus 1, 2 and 3, right? And all these values will be there with you in the previous step itself. For assume that, like, for example, if you're going when I is equal to 10, that is, you're going to compute register word for the step number 10. Yeah, if, for example, if the step is starting from 0, this is actually 11th step. Okay, numerical base is 10th step means you'll be taking AI minus 4, that is A6 plus Fi of A9, comma A8. This is actually A. Then A7, right, plus M, W, I value is 10 here. I'll come to this one then next later. Plus C10, this is a step. You will see what is each and every step is going to do. And all this addition symbol denotes your XOR operation. So as I said, for all the computation cryptography is coming into picture, all these things are XOR operations, right? So you'll be taking the 4 register words. First A6 is taken, then I'm going to apply a Boolean function Fi, right? So when I is 10, it is coming in this step. The I equal 10 lies in this one. So you'll be using if function as a Boolean operation here, and you have this if operation of x, y, z. We just saw this one, right? How this if operation works. You'll be applying your if operation here over, this is nothing but your x, y and z here, the 3 register words. Okay, after computing this one, then you'll be going with the XOR operation with MW10. So this MW10, M is nothing but your message word. We just saw this one here, these words M0, M1, M2 up to M15. Here we named it as MK, there they called as MW, that is a message word. Okay, MW, and I denotes, here in this case it is 10 means, so WI. So here why this I comes in the picture, in the sense you are going to take a message word, but this 10 denotes the permutation of the message block. That is, for I is equal to 10, for I value ranges from 0 to 15. Okay, this is your permutation table. That is permutation. You can able to see all the values are simply kept the same thing, like 0 to 15. All the 16 values are the same. If I value goes beyond 16, then you can able to see the permutation occurs. 0 is placed here, 1 is pushed here, 2 is here, 3 is here, 4 is here, and it's totally shuffled when I value goes beyond 15 here. Right. So for each and every values of I, based on this permutation block, okay, it's going to be permuted. I hope everyone know what is a permutation. It's like our transposition cycle. Then after this one, we are going to XOR with the constant C10. So constant value, since I is equal to 10, we'll be using this as a constant value in this case. After performing all these things, then I am going to perform a circular left shift. So SI denotes my circular left shift motion. So how many bits I have to shift left? Okay, it's depending upon this table, the size of rotation. When I is from, that is, this is for round 1, round 2 and round 3. When I is between 0 to 15, okay, the first bit will go for 3 bit left shift, then 7, 11, 19, again 3, 7, 11, 19. Like this for 14, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So 11 bit left shift will be happening here. Right. Is it clear, guys? This one, the operation. You don't really won't get any numerical on this one in examination. Just you should be clear with the concept how each and every step is running. Okay, thank you, Kashish. If anyone have any doubts, you can unmute and ask. Okay, assuming that you people are clear, proceeding. And this one, the update rule. So here the 4 register words A, B, C we usually used to take. Okay, initially we have to supply with the initial value, that is seed value. Okay, if you see this one, the scheme. Here I have to step, for first iteration, I have to give my own seed value, right? So this seed value is nothing but this one. These are this A, B, C, these. Right. So once after all the 48 steps have been over, you will be getting a final resultant as A47, A44, 45, 46. This will be again XOR with the initial value which you already fed in the first before the first iteration, and this resultant is nothing but your final hash value. So this is how they made it more robust, because we can't able to find the reverse operation here. It's very difficult to find the inverse of the hash, but yet they found a issue in this MD4, which is they proved that collision can be occurring in MD4. That's why it has been upgraded to MD5. Right. So if you see how the improved version of MD5 will look like, in the sense the operation has been same with only a few modification in the Boolean operation. So here they introduced 4 Boolean operation instead of 3. That is, they have introduced the if operation and they introduced this one G, H and Y. H is a simple XOR. Okay, this is a combination of AND operation, NOT operation and XOR operation. This one and this one. So they made use of these 4 Boolean operations in MD5. Right. Is it clear, guys? MD4 and MD5 improvement. Okay. Okay then. Right. Now we move on to next one. Next hashing algorithm, which has been built again from the scratch. The compression function is built from the scratch. That is a secure hash algorithm. In this, we'll be discussing SHA-512. That is the latest version which is in use. So SHA-512 version, okay, your message digest length is 512 bit. Okay, whereas in case of our MD4, we had 128 bit. In this case, it is 512 bit of digest. And this algorithm is also going to follow Merkley-Damgard scheme. Okay. You see how this one is going to be operated. Since you can able to see here, we have a entire message length. Okay, after padding and other stuff, it should be coming into a multiples of 1024 bits, because here the basic building block of each and every message block we are going to form is made up of 1024 bits. Right. And here the seed value is made up of 512 bits, which will be given as an input from a compression function along the message block, which gives me output of a hash value, which is also 512 bit. It should be fed back until it completes the entire length of the message, and the final value is nothing but your message is the final hash value is taken here. So this is how your SHA-512 will work on. Now if you see the message preparation, how SHA-512 is going to operate, because SHA-512 has a limitation in the total message length which it can able to operate, not like MD5 where it can able to operate with infinite length. Whereas here in SHA-512, the original message should be less than 2 power 128 bit, or to be specifically speaking, it should be less than 2 power 128 minus 1. Okay. This is the maximum message it can able to process. So again, the padding and the length field, it is using a similar method what we just saw with our MD4 family. Here you have your original message which will be less than 2 power 128 bit, and here we are using 128 bit, okay, to convey the length of the original message. If you compare it with the MD4, there we used 64 bit to convey the length of the message in our MD4. Whereas in this case, we are using 128 bits to convert this one. So after adding your original message length along with this 128, if it is not coming within the multiples of 1024, then you will be going with your padding. Okay. In this padding, again, the first bit will be 1, and the rest will be followed with zeros. Right. So I have a question for you. If a number of what will be the number of padding bits if length of the original message? You have to listen to this very carefully. Length of the original message is 2590 bits. Can you people tell me the answer? So you'll be having your original message of 2590, and you have your extra 512 bit. 28, sorry. 128 bit for your length conversion, conveying the length. Okay, then you have to find me altogether it should come to a multiple of 1024. If it is not coming, then you'll be going with your padding bits. So kindly let me know what is the size of the padding bits required here. You can tell in the chat box what is the answer you're going to get. A54, yes, perfect, Kashish. So you'll be getting 354 bits, out of which how it will be parallel in sense. The first bit will be 1, and rest of the bits will be going with 353 numbers of zeros. Right. So this is an yes or no questions. Do we need a padding if the length of the original message is already a multiple of 1024 bits? Yes or no? Can tell in the chat box. They're saying the length of the original message is already in multiples of 1024. In that scenario, do I need a padding bit or not? Yes, yes, Kashish, you are correct. Because we'll be adding the next 128 bit at the end to make it as a, to convey the length of the message. So at that time, it will be, it will not be a multiple of 1024, which will lead to a addition of padding bits. Right. Now, how here the words are going to be used in for SHA-512? Here there is a small modification compared to a conventional ways of representing words. So here we have 16 words in the message block, and 16 words, each of 64 bits. So it will be giving of 1024 bits. Can anyone tell and how many bytes are sitting in the 16 words then? How many bytes? If 64 bits are there, can you tell in terms of bytes? How many bytes make this one word in this case? Previously we have only 4 bytes. Yeah, here I'll be getting 8 bytes. Right. Similarly, the message digest which we're going to get as output will be made up of 8 words, and each word made up of again 64 bit, giving me 512 bit as my output. Both your message digest as well as your seed value, both are going to be made up of 8 words in this case. Right. So now we move on to word expansion process. Why, sir, we need to go for word expansion? Because if you take this our SHFI, this one, The iteration is going on inside this compression function. Okay. Totally, we are going to do 80 rounds. Here we don't have a term called steps in this one. Simply 80 rounds or 80 steps, whatever you wish to call. Okay. So total 80 iterations will be going to happen inside single compression function. So this will be repeated until I complete the entire length. So in this input message word, we have only 16 words present in this one. So 16 words will be used for my first 16 iterations or 16 rounds, W0 to W15. Then for rest of the things, I have to expand these 16 words to up to 80 words. How we used to do for key expansion in our AES algorithm, similar way. So how is key expansion? Sorry, the word expansion is going to be done here in the sense they have a general expression here. So whatever the word you're going to find. So in this case, assume that okay, if you want to generate W16, okay, W16, we are in need of 4 more words. That is Wi minus 16. That is in this case W0. Then second word I minus 15. That is W1. Then Wi minus 7. That is W11. Sorry, W9. W9. Then I minus 2, which is W14. So I'll be taking this 4 words for the process of generating my next word. In this case, W16. So what we will do in sense, we will take Wi minus 16. In this case, as I said, W0, which will be directly taken here. And Wi minus 7, W9 will be directly taken for the XOR operation. Whereas your W1, which is Wi minus 15, and W14, which is nothing but my I minus 2, has to undergo a rotational shift operation. What is this rotational shift? Shortly called rod shift. It's going to do in a sense. If I say rod shift of L, M, and N, in this case, in this first case, okay, L, M, and N take the values of 1, 8, and 7. Right. That is, I'll take the word, this word. In this case, it is W1. I'll take W1 word. Okay, then I'll make a right rotation of bits. How many right rotation of bits will be decided with the size of the L value? If it is 1, so I'll be taking W1. Then I'll make a right rotation with 1 bit. Okay, then I will XOR. With again, I'm going with the second one. Again, rotation R means right rotation with M number of bits. So in this case, M is 8. So I'll be taking the same word W1. I'll make a right rotation with 8 bits. And again XOR. Last one is value of N is 7, which will go for shift to left here. So shift left in the sense, I'll be taking the same word. Then I'll be performing a shift left operation, okay, in the left direction with N here, the value of N is 7. So this is going to happen in place of this W1. Similarly, if you go with the next W14, last word, first, this is a right shift of 19 bits, XOR with right shift of 61 bits, and left shift of 6 bits. So all these things once manipulated, then I'll be XORing all these values and I'll be producing the final word here. Is it clear, guys, regarding this word expansion process? Okay, rotation and shifting is same thing. Yes, actually, why they use the term rotation and shifting in sense, for right shifting, they're using the term called right rotation. For left side, they're using left shifting, the term. That's all. As you said, rotation and shifting, or the meaning is same. Here, as per for their convenience, they're using right rotation, left shifting. That's all. Okay, gosh. So, anyone have any doubt on this one apart from this? Or if you need any clarity, you can ask me. If it is clear, raise your hand so that I will go to the next slide. So now, for example, if you're asking to show how W60 is made, if in examination if you ask, then you have to get me this expression. This is more than enough. Okay. Don't worry, you won't ask giving your word and do all this stuff. If you want to ask, we'll ask any one of this one. I at least go tell me answer for odd shift this one or odd shift on this one. Okay. So here the each word will have a range from, in this case, from for W16 to W79. We'll be using the same procedure here. Now we go into message digest initialization. What I'm speaking here is nothing but the seed value. How we had ABCD in our MD4. In this case, we are going to have 8 words. Each word of 64 bits, right? As my seed value. And these are the 8 words starting from A0, B0 up to H0. So how these hexadecimal values have been generated here in the sense, okay, here they are generated by using the first 8 prime numbers. I hope you have the calculators with you right now. So what they will do in the sense, uh, for example, assume that if you want to value of D, D naught they want to produce. That is fourth one. 1, 2, 3, 4, 7. So can you people tell me the answer for 7 with respect to at least 5 decimals? At least for your understanding, I'm going with 5 decimals. In the chat,
2.64575.
2.64575. Right. Okay, perfect. Now I want one more thing you people to do. Now I'm omitting the whole number. I'm going to take this decimal round, that is 0.64575. Can you people, okay, as for your understanding, can you people take, okay, first 3 values and tell me the binary equivalent for it? You can post in the chat box. 0.645, this just take 645, convert them into binary. Actually, process is something, but they will be converting all the decimals into binary. And if they convert this binary into hexa, or if possible, if you can able to convert this all integer values directly into hexa, also no issues. If this hexa value is nothing but what is present here. Just try and check. So like this only they will be generating for all the first 8. I mean, using the first 8 prime numbers, they are generating the register words, 8 register words. So not in this case as a register. This is 8 words which will be used as a digest initialization values. Right? Is it? I hope it is clear. Right. So now we move on to the operation. What's going to happen inside the compression function? So this is our initial values. So in this case, if you have this one's A naught, B naught, C naught up to H naught, if this is the initial value, these things will be sitting there. Oh, sorry. Right. Then comes your round 0. For round 0, you'll be supplying with the W naught. Then we have a round constant K naught. I will come to this round constant separately later. Okay, this is a round constant. Okay, and these are nothing but your words. So first 16 rounds, no issues. We have the words from the message. After that, we'll be using word expansion. Then we'll be using it. So inside this each and every round, the compression function is going to happen. We'll see what is happening inside this one. Okay, so this will be repeated for 80 rounds, that is up to 79. And the final output which is going to get, that is if you have A79, B79 up to H79, is going to be XOR with the initial value here to give me the final digest value here. Right. So this is how the process happens inside the compression function. Right. I hope you people are clear with the structure of the compression function. If it is clear, raise a hand, because then only you can able to understand what is going to be happening in each and every round. Right. Now we move on to the structure of each and every round in SHF-I2. This is more complex when compared to our MD5. You can able to see. I'll show the expanded version in this slide. So generally, if you have this is like assume this is round 1. Okay, how this from round 1 to round 2, how this conversion is going to happen in a sense. Okay, whatever the values of A is going to be sitting here, it will be pushed to B, B to C, C to D, E to F, F to G, and G to H. Okay, the main function here is nothing to generate this A and E using these values of A, B, C, D, E, F, G, H or previous round. Okay, how this is going to happen in the sense? First, assume this one. You'll see first the mixer one, okay, where you're going to get the values of A. This is nothing but A, B, C's are nothing but the inputs from the previous round. Okay, I'm taking A, B, C, applying the majority function. Then I'm taking A alone. Then I'm going to perform a function called rotate A. So rotate A in the sense what it is going to do in the sense this is the operation going to happen. I will take the word A. Okay, then I'll make a right rotation of 28 bits, like how we did for our word expansion. Again, this is XOR with, again I'm taking the word A, right rotation with 34 bits, XOR with the word A will be taken, again it will be rotated with 39 bits. This values, these numbers are fixed, 28, 34 and 39 is fixed for all the 70 rounds. Okay, so whenever I say rotate A, all these three operations going to happen and our XOR is going to be done. And majority is going to happen like this. So once the output, whatever you're going to get here is going to be XOR here. Okay. And the output here is taken as output of a mixer 1. Okay. Now we move on to mixer 2. In this one, we are having 4 inputs H, E, F, and G. But here I am taking E, F, G for the Boolean operation. In this case, it's called conditional operation. The conditional operation is nothing but this one. X and Y XOR with not of X and Z. Right. And rotate E. Rotate E in the sense I hope everyone remembers now. Rotation here. So the output here is taken. The output of this one is taken. And in this mixer 2, the H word is again taken and XOR along with your word of that particular round and the round constant K. So here we have totally 5 inputs going to be XOR and to get me the output of a mixer 2. If I XOR the values of mixer 1 and mixer 2 directly, I will be getting the value of A for my next round. And only if I take the mixer 2's output and XOR with the D, because here you have A, B, C, D is here, then comes the E, F, G, and H. So you can able to see all the 8 words have been inward to create the new values of this A and E. Right, this is the operation going to happen inside this compression function. This will happen under this one round. Like this, it will run for 80 rounds. Here, what is happening here?
Excuse me, sir.
Yeah, Kashmish.
Sir, this is only one round, right?
This is only one round. Yeah, like this,
So,
80 rounds will go for compiling one block of this 1024 bit.
okay, so sir, in this, like we're taking the input as A, B, C,
Yeah.
and finally when we get the output, it's only one output. So, like for the second round again, what are we taking as the input?
No, actually here we are getting two outputs as A and E. Okay, and for next round, this is the thing. That is what I am just saying. This is from round one. So round one values are this one. One second. So these are the round one values A, B, C, D up to H. Okay, and these values are sitting here. A, B, C, and all this D, E, F, G, H. So using this one, I am generating the outputs A and E. So I'll be substituting, sorry, the values of A here and E is put here. Whereas for next round's output, the value of A is here is directly pushed to place of B. So B will be coming to C and C will be coming to D. E will be coming to F, F will coming to G, and G will come and sit to H. So this is the new values of A, B, C, D, E, F, G, H for the second round.
Okay, sir. Okay.
Okay, in this case, we are just shifting the values of A, B, C and E, F, G in the place of B, C, D and F, G, H. Only A and E are generated using this expressions. Is it clear?
Okay, sir. Yes, sir. Got it.
As I said, I mean, I just not to make it more clearly, I just put these things in the next slides. Right. And the 80 constants, as I said, this round constants, we had creating 80 round constants, and these 80 round constants are also created using first 80 prime numbers, but okay, but here there's a small modification they made. For round constant, they instead of taking a square root, they took cubic root. For example, the 80th prime number is 409, and if you take the cube root of 409, you'll be getting the answer 7.4229 and goes on. So if you convert them into binary, you'll be getting this one, and hexa, I'll be getting a 7.63 and goes on. So they took this part alone and they kept it as this one, the 80th round constant. So in this case, they'll go for the cubic root, right? There's a small example for you to easily understand this majority function and the conditional function. First, I will go with the majority function, right? So in this case, we are just taking very simple numbers, hexadecimal values for you to understand. Okay, we have the values A, B, and C. Okay, A is nothing but hexa value is 7, and this one is K, and this one is E. Right. So I want you people to let me know the answer for, convert this 7 into this 7 is in hexa value, okay, into binary. Tell me what is the value in 4 bits. Because if you convert them in binary, you'll be getting 4 bits. A and E. Kindly tell the values in binary in the chat box. The 3 binary values, 7, A, and E. Kashish, only Kashish, Kashish and myself alone, we are learning cryptography, it seems. Is there anyone who got the same answer or anything? Examination, this majority function, conditional functions will be worthy for 10 marks. We'll be giving some bigger numbers. For understanding, I just kept a smaller values here. Okay. So you'll be getting the values as 0, 111, 1010, and 1110. Right. Now you have to take the majority functions. I'm going to apply this majority function here. Easy way to remember here. Okay, generally we'll be applying with three values alone. So I'm taking the first bits. There's 0, 1, and this 1 is taken here. 0, 1, and 1. So among these three, which binary is been majorly there, so that's the output. And second bit I'm taking, right? That is 1, 0, 1. So if you take 1, 0, 1, the output again comes as 1. Similarly, if you go with your third and fourth bit, you'll be getting the final answers like this. So in this case, 3 ones, so obviously answer is 1. 1, 0, 0. In this case, answer is 0. So the final output is 1110. If you convert into hexa, that will be the final value. This is the easiest way to do the majority operation instead of going with this operation of A and B, XOR with B and C and C and D. No need to go with this one. Simply convert them into binary, take the values, just check which is majority there and put the final value as output. Is it clear, guys, regarding this majority function?
So in the fourth one, the fourth bits are 1, 0, and 0. So
Yes.
the majority is in the sense like.
Okay. Among these 3 bits, which bit is repeating more times?
Okay, sir.
The number of, either you'll be having 1 or 0, which is repeating more. So in this case, 1 occurs twice, so answer is 1. In this case, the 1 occurs twice, the answer is 1. In this case, 1 occurs in all 3 instances, so answer is 1. In this case, 0 occurs only more time compared to 1, twice, so answer is 0.
Okay.
This is like a shortcut. This is a shortcut way to do this majority function. That's all.
Yes, sir. Okay. And also, sir, the sizes of A, B, C are same only, right?
Yeah. Oh, you're
Okay.
asking This one, I mean, if
The
you are
input
generally, if I
ABC.
give in this input ABCs, right?
Yes,
All
sir.
will be in same size. Don't worry.
Okay, sir.
I hope you are clear with the majority function. Now we move on to conditional function. Yeah, so there is also shortcut here. So here I have shown you the converted version. If you convert 9 into binary, you'll be getting this one and A and F. Okay. I'll just reveal the answer first so that at least people can able to guess. So here, for example, we have inputs as E, F and G, right? So this is E 1, 2, 3, 4 bits for E, right? And for F, these are the first bits 1, 2, 3, 4. And for G, these are the first four. These are the 4 bits. So if I say F1 means I mean in F the first bit. G2 means in G second bit. G3 means I mean G third bit. F4 means in F the fourth bit. Right. I hope the logic of this F1, G2, G3, G4 is clear. Right. What I am representing. Now, can you people able to guess how they got this value? That is why they took this F1, why they took this F2, G2, G3, and F4. Any guess? I'll give you a minute to analyze this one. You want to guess, guys? Or shall I reveal? Okay, simply just an easy way to remember for conditional operation. So conditional operation, the output was decided upon the first input. In this case, the value of E decides the output first. So if you take the first bit of all these three, so 1, 1, and 1. It's a conditional output. If your E is having value of 1 means you have to take whatever the output value for F is going to be sitting here. So this is the value of F and this is the value of G. So simply take whatever the value F is holding and put it here. If I'm taking all the second bits 0, 0, and 1. So here this is value of E, this is value of F, and this is value of G. Whenever this is value of T goes to 0, go with your output of a third. That is simply speaking, this is the first input, second input, and third input. When first input having the value of 1, go with my second things as second inputs value as output. If my first input value goes to 0, go to my third input values as my output. That's why if E becomes 0, whatever the value is sitting for G, take that as output. In this case, again E is 0. The value sitting in place of G is G, third bit of G is again this one. And in this case, the value of E is goes to 1. So whatever the value sitting in place of F here is F4. The answer comes to 0. The concept.
Yes, sir. Sir, if you have an 8-bit number,
Okay.
then again the numbering starts from the left only, right? 1, 2, 3,
Yes,
4.
yes,
Right.
yes, yes.
Okay, sir. And sir, for the previous case,
Okay.
the majority one, in case of an 8-bit number, if there's a tie between the number of zeros and ones, then
No, even if you have 8-bit also, here you're going to compare only 3 words. So obviously, like you'll be taking only 3 bits always, whatever the
Okay, sir.
size may be. But your iterations like this one, this is first bit, second, third, and fourth. Here will be continuing with fifth, sixth, and seventh, and eight. So no issues.
Okay, sir.
This confusion may occur only if you have even number of inputs, but the operation of majority and conditional operation does not apply with more than 3 bit as input.
Okay.
You'll be getting 1110, and this is the N7. Right. So, if you analyze for SHA-512, okay, it is expected to resistant to all attacks, including collision attacks. Till date, SHA-512 is found to be more robust. So that's why after 94 or 96, I think so, they didn't modify SHA-512. We still are using SHA-512. So with this, we are concluding our secure hash algorithm, and I will conclude today's session also with this one. Right. So anyone have any doubt in today's class, you can ask me now.